Hello everyone, my name is Kazuma. I'm a graduate student at University of Tsukuba. I'm very glad to be able to talk to you today. I'd like to talk about the asymptotic analysis of the modified Erlang-B model and some results regarding the stability condition and the uniqueness of the stationary solution to approximate the mean number of sensing as secondary users. This work is joint research with my supervisor, Tuan Phung-Duc. Here is the outline of my presentation. First, the introduction and overview of cognitive wireless networks. Second, my model description and assumptions. Then, I will explain the first-order asymptotic analysis to derive the normalized number of secondary users. Using the asymptotic diffusion method, we obtain the function which expresses the normalized number of secondary users in the orbit. After that, I will show the stability condition of the model and the uniqueness of the fixed point, which also represents the mean of the number of secondary users in the orbit. Lastly, I offer some numerical experiment results. Recent internet traffic has increased explosively due to the demand for smartphones, tablet computers, and other electronic devices. As a result, there is a shortage of wireless resources, that is, radio frequencies. Cognitive wireless networks, CRN, is expected to leverage the bandwidth shortage problem. These technologies were deeply studied by various approaches, such as Poisson processes, machine learning, and queuing theories. In this presentation, we analyzed the system using the modified Erlang-B model. In the next slide, I'll introduce the overview of cognitive wireless networks. In this technique, there are two types of users: secondary users and primary users. SUs are non-licensed users, and the SU senses the channel not occupied by PUs and transmits in the available channel. There are mainly three types of methods: interweave, underlay, and overlay access. In this presentation, we only deal with interweave access. In the next slide, let me explain the flowchart of our model. First, we assume that there are two types of users, as in the previous slide, and each user arrives at the system which has C servers according to Poisson processes, with rate lambda 1 and lambda 2 respectively. The transmission times of PUs and SUs are exponentially distributed and with parameters μ1 and μ2 respectively. The arrival process of both user types and the service types are assumed to be mutually independent. A newly arriving PU occupies a channel unless all C channels are occupied by other PUs. Otherwise, a newly arriving PU is blocked and leaves the system. Hence, the model can be treated as Erlang-B from PU's point of view. Arriving SUs must enter the sensing pool and sense for available channels. The sensing time of the SUs follow the exponential distribution with rate sigma and do not depend on other SUs. When a SU finishes sensing and cannot find an available channel, it will stay in the pool for another sensing with a probability p. Otherwise, it leaves the system with probability 1 minus p. When a new PU arrives at the system when all C channels are occupied by other SUs, and PUs, the PU terminates the transmission of an SU and uses that channel. The interrupted SU must enter the sensing pool to sense again. The sensing pool is assumed to be infinite. As the previous slide, the behavior of SUs is similar to the retrial phenomenon in retrial queues. We generalize the result and consider the number of secondary users in the orbit with respect to probability P. We focus on the situation where it takes SUs a long time to sense channel availability, apply the asymptotic diffusion method. Due to the complexity of calculation, the asymptotic diffusion method complements the other methods such as QBD approach. In this slide, I will talk about the notation of a model. First of all, I denote some variables as follows. Then I construct a three-dimensional Markov chain. Our goal is to obtain the distribution of N1T and N2T, discrete probability density function, and expectation of IT. But in general, it is difficult to analyze the three-dimensional Markov chain, so we have to consider alternative ways. In order to obtain the expectation of IT, we use the property that sigma I tau over sigma converges to a deterministic process x tau when sigma tends to 0. Here, x tau is the solution of derivative of x tau by tau equal ax tau. For simplicity, I redefine x tau equal x. X is given by the equation 1. Here, the first and the second term means the increase of the size of the orbit. The third and fourth term expresses the decrease of the size of the orbit. And the S1, S2, S3 means the sum of the probabilities. Here, I'm going to review the main points again. About the distribution of N1T and N2T, Rn1 and N2x is the asymptotic probability of N1 and N2. Rn1 and N2x is the probability that the number of PUs and SUs are N1 and N2 respectively in an MMCC where arrival rates of PUs and SUs are lambda 1 and x respectively, as figure 2. Next, the discrete distribution of IT, we use the 1 over square root sigma multiply sigma I tau over sigma minus x tau converges to a diffusion process. From x tau, we can obtain the expectation and distribution of IT. Next, I will talk about the main theorem. The system can always be shown stable when probability P is less than 1 via the theory of Lyapunov functions. Here, we show that the limit condition, the limit as x tends to infinity of Ax, is less than 0 is consistent with the stability condition by the previous work. In the slide, it is only necessary to show that Ax decreases with x. So we write the equation 1. We have the transformation as follows. Here the first and second term doesn't depend on x. That is constant. And the third term means the throughput of all users, and the fourth term diverges to infinity as x tends to infinity. Hence, the limit is negative, holds for all parameters with p is less than 1. So, hence, we prove the theorem for 4.1. In the next slide, I'll explain the uniqueness of the function. So finding the kappa such that a kappa equals 0 means the expectation of the number of secondary users in the orbit in the stationary state. And the fixed point is used to derive the stationary distribution of n1t and n2t. But the uniqueness of the solution was not proven. In the next slide, I'll give the proof of theorem 4.2. It is clear that the initial value and the limit condition is we have the condition from theorem 4.1. From the intermediate value theorem, there is at least one value kappa in real positive numbers, for which a kappa equals 0. So it is necessary to show that ax monotonically decreases with x. Apply the proof of theorem 4.1 once again. The latter two terms of equation 2 monotonically decreases as x increases. Hence we prove the theorem 4.2. In this slide, I will illustrate the mean number of SUs in the orbit for a single server. We can see that the larger the probability P is, the more SUs there are in the orbit. This trend is due to the higher chances that an SU stays in orbit when it gets blocked. When lambda 2 is small, the difference between the values for each P also becomes smaller, and the difference is more significant with larger lambda 2. Furthermore, we can interpret that the crowding of the orbit increases the demand upon available channels when the probability is high. Figure 6 and 7 show the average number of SUs in the orbit against their arrival rate for C equals 5. Figure 6 shows the slight differences between each P when lambda 1 is small. In contrast, the bigger lambda 1 is, the bigger the differences are. Because the number of SUs in the orbit is fewer when P is lower, they have more chances to occupy the channel on first arriving. The greater the probability P is, the bigger the differences become because the number of sensing SUs increases and the SU is more likely to be blocked. Finally, we compare the transition of the behavior between simulations and x tau over sigma in figure 8. We can see that the simulation results evolve around x tau over sigma over time. We can see that x is appropriate enough to approximate the normalized number of SUs in the orbit. In the summary, we analyzed the behavior of secondary users in a modified Erlang-B system using the asymptotic analysis under sigma tends to 0. We derived the probability distribution of the states of occupied servers under the first order approximation. Using the method of asymptotic analysis, we obtained the stability condition, which is consistent with previous work. Besides, we showed that the uniqueness of the fixed point kappa such that a kappa equals 0 to derive the stationary solution of x tau for our model with P is less than 1. We also performed some numerical experiments to investigate the distribution of the states of servers and the number of SUs in the orbit. Thank you for your listening.